Welcome back. Let's talk about Y to delta transforms. So I have a little circuit here with an ideal current source. It's putting out 2 amps. There's also a voltage associated with the current source, but this is an ideal current source, meaning that it's going to put out 2 amps no matter what. Now there will also be a voltage associated with this current source, but the voltage will be whatever voltage is needed to maintain 2 amps. That's what we mean by ideal. But keep in mind that a source of any type is going to put out a current and a voltage. It's just usually we lock down one of those things. So this is a current source, which means we're locking down the 2 amps to be always 2 amps. All right. Now there's a resistor network here with a 20 ohm resistor, 28 ohm resistor, a 10 ohm resistor, a 5 ohm resistor, and a 105 ohm resistor. And we've got nodes, let's label these A, B, and C. And there's another node in the middle here, D. So we've got simple series connections like this, where resistors will share a single node in between, and then there's nothing else coming off of this node. So this is what I'm calling simple series. And then we've got simple parallel, where 2 resistors share 2 nodes, and there's nothing else in between these 2 guys. So we don't have that, either one of these cases in here. We don't have, like, these 2 resistors, the 10 and the 20, are in series, but there's also this guy coming off of here, which sort of screws up the simple series. And then these, let's see, these 2 guys are almost in parallel in that they share, you know, if it wasn't for this supply, they would be in parallel. So there's really nothing that's in just simple series or simple parallel. So we can't do any simplifications, which is what we're trying to do. So we want to use a Y to delta to simplify all the way to 1 resistor. Okay, that's the first thing we want to find. The second thing we want to find is use the one resistor equivalent to find V0. All right. So we can't do any simplifications using just series and parallel because we don't have any thing that's in just simple series or simple parallel, so we have to use our Y to delta thing. So what's in a Y configuration and what's in a delta configuration, right? Where are the deltas, where are the Ys? Let's find them. There's a delta up top, right? There's these 3 resistors here that are connected between A, D, and B. Right, these 3 guys, that's a delta. There's another delta over here. These 3 dudes are connected between C, D, and B. And there might be another one, maybe going around the, no, I think that's it. So those are the 2 deltas, but there's a Y in here, right? These 3 right here, the 20, the 10, and the 5, they're connected in a Y configuration between A, B, and C. So this delta Y transform, I'm not sure where to write it, but this delta Y transform is in A, B, C, is between, that's the Y we're looking for, is the A, B, C, okay, because there's a Y in here. And if you look back on the math for a delta to Y transform in the notes, there's nodes A, B, and C. There's also a node here that's not labeled, because it disappears. When we convert from Y to the delta, this middle node disappears. Okay, so all of these equations which we're going to use are referenced in terms of A, B, and C, and 1, 2, 3. So we have A, B, C, 1, 2, 3, we have A, B, C, and then again A, B, or A, B, C. Okay, C being opposite, this RC being opposite there, and RA being opposite there, and R being opposite there, and R1 being next to A, R2 being next to B, and R3 being next to C, and we got all these equations in here. So let's do that. So I can apply the y to delta graphically, and here's what I get. So node A stays there, and this guy is left out of the transform over here, and B stays there, and C stays there, and this guy over here is left out of the transform. So the 28 ohm and the 105 ohm, these two guys are just hanging out. But the three guys between A, B, and C are going to be transformed from their current Y configuration into a delta configuration. Right? That means this guy right here next to the A node is R1. And this guy right here next to the B node is R2. And this guy next to the C node is R3. This guy opposite the C is RC. This guy opposite the B is RB. And this guy opposite the A is RA. Right? Then we apply the math formulas we have. So RA is given by R1, R2 plus R2, R3 plus R3, R1 over R1. That's the formula we have. And plugging in the values we have, R1, R2, R3, and such. Plugging in the 20, 10, and 5 into here as appropriate, you end up with 20 times 10 plus 10 times 5 plus 5 times 20 over R1, which is 20. This works out to 350 on the numerator over 20 on the denominator, which is 17.5 ohms. That's RA. It's 17.5 right here. Ohms. Okay, repeat for, oops, wrong one. RA is 17.5 over here, ohms. So repeat for RB and RC. So RB, the formula for RB is going to have the same numerator. So we already solved that, it's 350. And you put R2 on the bottom, which is 10. So this is going to be 35 ohms. Okay, and RC is going to have the same numerator, and you put R3 on the bottom, which is 5 ohms. So that's going to be 17.5, half of that one. Okay, so this RC happens to be up here. This is 17.5, and so 70. Oops, I multiplied instead of. This should be 70 ohms. Whoops. This is 70. And this is 35. But we're going to redraw it pretty soon. Okay. So what we did is we applied a Y transform between A, B, and C, and turned that into a delta transform between A, B, and C. Or we applied a Y to delta transform to the Y between A, B, and C, and we turned that into a delta between A, B, and C. It's a better way to say it. And that transform from Y to delta sort of cracked open the circuit, so now we can do simplifications. Simple series and parallel simplification. So right now these two guys are in simple parallel. Likewise, these two guys up here are in simple parallel, right? Because these two guys share node AB, and these two guys share node CB. So we can simplify more. We could write out more. So let's see, where's these two guys? They're in parallel, so the 28 is in parallel with the 70, and that ends up being do the product of this over the sum. So this ends up being 70 times 28 over 70 plus 28, which is 20 ohms. So that's this guy up top, these two guys up top. Now these two guys over here are also in parallel. So that's 17.5 is in parallel with 105. And that works out to 15 ohms, just skipping the steps here to get done quicker so we can get finished. Then you can redraw this thing after those two transforms, and you end up with this. So A stayed there, B was over here, C was over here, and so these two guys we replaced with a 20 ohm. These the two guys between A and B. And the two guys between B and C we replaced with a 15 ohm, so that's over here. And the 35 guy was just hanging out watching what's going on. Okay, so now we have more simplifications we can do. These two are in series, so 20 plus 15 is 35 ohms. And now the 35 ohm between A and C, right, if you redrew it, which you could if you wanted to. But if you redrew it, you'd have a 35 here, and then that would be in parallel with another 35. So you end up with a 35 in parallel with a 35, which ends up being, well, 35 times 35 over 35 plus 35. It ends up being 17.5 ohms. So the final simplified circuit is just between nodes A and C. All of these guys between A and C, we'll just draw it over here. Between A and C, 17.5. And the 2 ohm guys there, and here's V0. V0 is still there because V0 is between nodes A and C up here. And here it is again. This is a simple problem where that happens. We're going to see it in more complex problems, so I'm pointing out. The original signal V0 is referenced between nodes A and C. Those nodes are still here, they haven't changed, so V0 is still the same. And we'll see later where you got to watch out for that kind of thing. But here, it's fairly simple. Well, so this is the first answer. That's this first answer right here. Second answer, we want to find V0. So Ohm's law, V equals IR. So V0 is going to be 2 amps. 2 amps going around here, going through 17.5 ohms. That's 35 volts. Okay, see you later.